All right. So one more thing, some of the students has brought up about this minimum reinforcement area on the one-way slab. So specifically, if you go back to ACI code, the one-way slab is in chapter 7. Chapter 7. So the minimum reinforcement was mentioned in chapter 7.6.1, 7.6.1, and the number is slightly lower, which is 0.0018. Instead of 0.002 that we talked about. Okay, so I want to show you a little bit my screen so you can see it.
Or maybe a back screen.
Where's my code?
Unlike the doctor, I prescribe exercise. I keep a chart for each patient and write down how many repetitions.
So if you see from my screen, this is the ACI code, and there's a 7.6.1.1. There's a minimum area flexion reinforcement 0.0018. That's slightly lower than the 0.02 that we mentioned in our lectures. Okay. Now the reason behind it is our lectures 0.02 was based on the revision code, not from 318. So there was a typo there. Okay. Now that's not a big deal, but the big deal now is that we have two different numbers, which one to use. Okay. So I went back and forth compared to the previous version of ACI and the current version. This number has now changed before. So I think this is still the old number. In line of that, if you use 0.0018 for your minimum reinforcement area, it's also okay. If you use 0.002, it's also okay. So both numbers are fine for now. Okay, and I'll get more clarifications when I attend the conferences. I don't know how it's going to happen this year, but if I'm going to attend the conference, I'm going to bring it up to see if there's any consensus about this requirement. Okay, but for now, if you want to use 0.0018 or 0.002, both numbers okay. All right, both numbers okay. Okay. Oh, sorry. There's a note on the 0.08. That's actually 0.018. There's a typo there. Okay, Anna. So I caught that, and I will correct that and upload our notes on Canvas as well. Okay, it's actually 0.0018. Okay, there's a typo there. Okay, all right. So so that's fixed. Either way, if you use 0.0018 or 0.002 should be fine. In reality is that if you use 0.002, that's higher than the 0.018. So we should be safer. We should be safer. Okay. Now, again, I will bring it up to the conference to see the consensus of that, what happens there. And maybe at the time, I hope it's not too late, but if that happens after our courses, and then I have to maybe send you other things about it. If you use 0.018, sorry, that's a, let me send you the message. It is 0.018, but if in homework, you by accident, if you use 0.008 instead, it's not going to be penalized. Okay, it's not going to be penalized because this reinforcement area is bigger than the 0.018. Yeah, this is, sorry, my typo, 0.001. Yeah, so this is not going to be penalized from your homework. Okay, but in exam, I prefer you use 0.002 for exam. This is what I prefer, but 0.0018 is okay as well. Okay. Okay, so this is the minimum reinforcement for the slab. Okay, now coming back to our main lecture, we have several things left. We have the deflection, which we'll probably finish today. And we also have the column, which we're going to be focused during the next couple of lectures. And right afterwards, we'll come back to the bonding between reinforcement and concrete. That'll be the last of it. Okay, so I know we have 2 weeks, roughly a little bit more than that, maybe 2 weeks of lecture time. Our final lecture day is on May the 8th, May the 8th. And for the final, it's gonna be an accumulated final. First of all, it's gonna be an accumulated final. So I would like you guys to go over all the content, but 60% of the final exam will be on the last segment of the lectures, which is in the column, and also on the serviceability that we talked about, the cracking, the deflection that we're going to talk about today. 40% will be a quick review of what we had covered before. Okay, so please start review the lecture notes as soon as you can. Okay, now to help you out, I'm gonna hold a periodic review session on every Tuesdays. No, there's no midterm 3 anymore. Okay, it's gonna be final now. So we have 1 midterm and midterm 1, 2 midterm, midterm 2, and the final. Okay, those is going to be our arrangement. And if you look at the syllabus, I believe that's the arrangement. So for the let me lost train of thought there. Okay, so for the review session, so we're still gonna do review every Tuesday in office hour. I found it very effective actually this Tuesday, so I'm gonna hold it again next Tuesday and the Tuesday afterwards. Okay, so every Tuesday 2 o'clock we do a review / office hour. Okay, all right. So that's about the items left from previous lectures. So I'm gonna share our screen. Verify, I said May 8th is the last day of the final. No, May 8th is the last day of class, last day of class. If you look at the calendar of Missouri S&T, May 8th is the last day of class, okay? I believe the final week is May 11th, all right? But correct me if I'm wrong, okay? You can cross-reference the calendar that's there online, okay? And I haven't decided what kind of format we have to use for the final yet, per se, because I'm still debating whether we should do a closed book and open book. I'm leaning towards right now to open book, but we'll see, right? We'll see, okay? All right, so let me open up the chat so I can see you. All right, okay. Now, just a second, let me see here, okay. Let me go to my notes, and this is where we left at in terms of deflection, okay, deflection. Now, here, when we talk about deflection from last lecture, we said the beam has several stages or have several areas. When you have an applied moment, a district moment like this, okay, so I'm gonna use my little mouse here to show that. When you have a distributed, let me go with that, maybe it's better this way. When I have a distributed moment like this, okay, it's a bit too wide maybe. Oh, sorry. Okay. When I have a distributed moment like this, okay. Now the moment diagram looks like a parabolic because it's a second order equation. And when that is a parabolic, it will have parts of it exceed the cracking moment, which is here, okay, which is, which is this region, exceed the cracking, okay? And then also I have a distributed moment that within this region that is lower than the cracking moment, that is lower than the cracking moment, okay? So that means in my section there are, well, there is a section that has a moment inertia that is cracked moment inertia, okay? And there's a section here that is a uncracked moment inertia, okay? So that means I cannot use one moment inertia to calculate the moment of inertia for the whole beam to calculate the deflection, So to do so, I have to use an effective moment inertia, okay? So what is this effective moment inertia? So effective moment inertia is calculated through this equation here. And this equation on the right is actually an empirical equation. It's an empirical equation. That is to say, this is not theoretically derived just by data, okay, by fitting. So this equation actually shows that is a function of MCR, which is the cracking moment, can be calculated using the modulus of rupture, which is FR, and IG, which is gross moment inertia divided by YT. And for those of you who start to have a for memory here, this is neutral axis, and when I have a positive moment going like this, right? And the bottom should see tension. So YT is the distance from neutral axis to the bottom fiber right here. Okay. And IG is the gross moment of inertia for the whole section, okay, for the whole section. Okay, all right. Now, don't forget, if I need to convert my steel, I have to convert my steel in terms of little extra wings on the outside, okay? Extra wings on the outside, okay? All right, so the rest of the part is 1 minus MCR divided by MA to the power of 3 here. And then outside, there's a cracking moment inertia. For the cracking moment inertia, right, we're going to show you how we calculate that, okay? But from last time, we showed you how to calculate the cracking moment inertia in terms of transform section. Simply remind you that it's basically just the O section, but you have the compressive zone, which is KD. And we did have a formula to calculate KD, right? And we convert the steel into N multiple AS, where AS is the reinforcement area, N is the modulus ratio, which is equal to ES over EC, right? That's the N. That's the N. Okay, so that's how we convert the cracked section to the cracked moment inertia. Okay, so that's the equation to calculate the deflection. That's the equation to calculate, well, moment inertia for deflection. But how do we take into account, right? How do we take into account other things? So this I effect right now is actually just one section, right? One section, which is here, I cracked and IG, right? What if, right? I had different shape. I have a different shape, right? So for a continuous beam, IE can be different in terms of positive moment, use a better word here for, and for negative moment. Okay, how so? For example, if I have a T-beam, okay, and if I say the positive moment, which is bending this way, and the compression is on the top, and assuming that the compression lies within this flange here, I'm just gonna use this dashed line here to show the compression zone. And so I essentially have a section just like this. Okay, and this is for the positive bending moment, Okay, and now if I have a negative bending moment, okay, negative bending moment, which is this right here, okay, so negative bending moment. Now my compression zone is going to be the bottom, so I have a compression zone, something like this, okay. So what happens? What happens that you cannot use the same IE anymore. The IE will be different. Okay, so from ACI 318, this is from 318, 24, 0.2, 0.3, 0.6. Okay. It says that the effective, use a different color, effective moment inertia has to be half of the effective moment inertia at midspan, right? Plus a quarter of the effective at the end. Okay, so this is illustration here. This is at midspan. This is at end 1 plus end 2. Okay, what does it look like? So basically saying if I have a beam that maybe in terms of column, let me draw this way. This is the column. Okay, so this section here, if I cut it, maybe it looks like this, and this is the compression reinforcement, and this is the tension reinforcement. Okay, so that is IE in the middle. And here, same section, but when I have a different compressive zone, so I'm gonna shade it. This is the compression, and this is compression. So this is IE 1, and this is IE 2. Okay. And the compression zone goes like this. Okay. So for a one beam across this span, I have 3 sections. I need to take the average to get my average effective moment inertia. Okay. So once you have moment inertia, you can calculate deflections. You can calculate deflection. So by the code, to calculate the deflection, right? There are several types of deflection. So calculation of deflection and also long-term deflection, okay? So there are 2 instantaneous and long-term deflection. So I want to show you a table here. Okay? So for the table here, I have dead load induced deflection. I have live load induced deflection, and both of them will have a different types of deflection to the structure. I have one called instantaneous deflection, and I also have a time dependent, which is long term, right? Time dependent deflections, time dependent deflections. Okay, okay, all right. So let me label them differently. Okay, so for the instantaneous deflection, I call delta ID. Okay, and for the long term deflection, I can use a coefficient lambda d multiply by the delta ID instantaneous deflection to get it. Okay, same time, I have a instantaneous deflection caused by the live load. I use the same factor to calculate the live load induced deflection. Okay, but be careful here. When I mention the live load, what I mean by this is sustained live load. We talked about this, right? There are several different types of live load. There are machinery that's going to occupy the floor for a long time. So that is a sustained live load. But there are live load, for example, like humans, right? We'll walk on it, and those are not sustained. Sometimes it come off, sometimes it stays. Okay, all right. So the instantaneous deflection here is easy to calculate, right? To calculate this, you just need the equation and also the moment inertia, i.e., we just calculate. All right. Now the difficult part to calculate is the long-term or time-dependent deflection, and this fellow right here, LD lambda d, right, is actually depends on the time. Depends on the time. Okay. So now we're going to show you what is this lambda d is all about. This lambda d is all about. So calculation of lambda d. Okay. All right. So by definition in ACI code, ACI 24.2.4.1. All right. So lambda d is an parameters called epsilon. Okay. Okay. And then 1 plus 50 rho prime. 1 plus 50 rho prime. Okay. And the rho prime, by definition, is the reinforcement ratio for the compressive reinforcement. So this is rho prime, AS prime divided by BD. Okay. So AS prime is the compressive reinforcement area of the compressive reinforcement. Okay, so in this equation, rho prime is the reinforcement ratio, right? The only parameter, epsilon or Kc, I think is a epsilon, but it's a Greek letter, right? So this is the time-dependent coefficient. This is the time-dependent coefficient. Okay. Matter of fact, you can find this in a table. You can find this in a table in 24.2.4.1, right? And then it will show you a table like this. Okay. I'll show you the y-axis in terms of parameter, and also the x-axis in terms of duration of load, how long the load has been applied to it in terms of months. In terms of months. Okay, so here, this parameter actually ranging from 0 to 2 maximum. 0 to 2 maximum. And bottom here I have 0, I have 3 months, I have 6 months, I have 12, 24, 36, 98, sorry, 48, 60, so on and so forth. And then this is 1 in the middle, and I have this nice table here. Nice table here, okay? And then the curve for this, let me put the grid line here so you see it better. Okay, so the curve actually looks like this. So it will cross this line here, okay? And we'll go somewhere like that and all the way to the end, approach to 2.0. Okay, so now when it passes a half year, which is 6 months here, I have a number of 1.2. When I pass a 12 months, which is right here, I have a number of 1.4. So this table is provided, okay? In an exam, we will provide you the table so you can actually read what is this number here? What is this number here? Okay, and then once you read this number from the duration of the load, you can immediately apply to this equation right here to calculate your lambda and to find out your long-term deflections, Okay, so with this defined, we actually have now the total equation form for the total equation. So equation for the total deflection delta total includes everything equal to a lambda coefficient, that is lambda from a time your load started to infinite, to forever, right? And multiply IAD, which is instantaneous deflection caused by the dead load, plus instantaneous deflection caused by the live load, and plus an infinity lambda multiplied by live load sustained caused the deflections. Okay, so this is the total deflection. This is the total deflection. All right, and specifically lambda infinity equal to this parameter plus, actually, right? And then this lambda from a time t0 to infinite equal to, oh, sorry, this is not 2 anymore. This is 2.0. 2.0 equal to 2.0 1 mass plus 50 rho prime minus, okay, this number here at time t0 divided by this. Okay, so that is 2.0 minus on top divided by 1 plus 50 rho prime. Okay. All right. So to calculate the total deflection, what you need to do is first, right, we'll show you the example, but let me try to explain here a little bit, okay? So first, we need to identify that at the time it started to have load on it, right? So T0 is time dead load applied. Okay, so once you identify T0, you go to the table to find your parameter epsilon, and then to find your lambda T0, which is actually epsilon T0 divided by 1 plus 50 rho prime. Okay, and then at time equal to infinity, so this is time equal to T0, and this is time equal to infinity, you find this C is naturally equal to 2.0, and this lambda infinity is actually 2.0 divided by 1 plus 50 rho prime. Okay, then lambda T0 to infinity equal to lambda infinity minus lambda T0. That is 2.0 minus CT time O TO divided by 1 plus 50 rho prime. Okay, so that's how we calculate the factors. That's how we calculate the factors. Ooh, sorry, not a whole lot of batteries. So that's how we calculate the factors to get the deflections, Okay, all right. So quickly, this is the total deflection equation. So we need to calculate the delta ID, instantaneous deflection caused by the dead load, instantaneous deflection caused by the live load. And these can be calculated using the IE here, moment inertia here. And then once we have that, we calculate lambda using this equation. And all we need is to look up the table to find out this C or epsilon value here, and to find out its corresponding lambdas, right? And then plug back in to calculate the total deflection, All right, this is a little bit complicated, right? It's a little bit abstract. So we would like to take a look at an example, right? Example. So here, let me show you the example how we calculate all this. Okay, so example, okay, for the beam shown below, okay, calculate the part of the total deflection. Not the whole thing, but the part of the total deflection, right, would adversely affect the partitions. Okay, all right. Okay, so let me explain to you what we're going to do with this, right? So first of all, let's show the beam, right? Show the beam. So the beam has a nice structure, right? It's a column here, and a beam joint here, and a column here. Okay. So just gonna draw the geometry for now. The column beam joint. Okay. Now the reinforcement. I have a compressive reinforcement on the top. See the different color. Black, a little bit thicker so you can see better. Okay. So this is one rebar. Okay. There's another rebar here. I have a continuous bar all the way. Okay, and to make sure I have enough bending resistance, I also have additional bar here. Okay, so these are the rebar reinforcement, right? Rebar reinforcement. And then let me label, I know that this is basically, okay, this is 4 number, it's too thin, so sorry. Let me change this a little bit thicker. Okay, this is 4 number 9 bar. Okay, plus a 1 number 11 bar. Okay, and this is also 4 number 9 bar and plus 1 number 11 bar. Bottom here I have 2 number 8 bars. Of course, it's the same 2 number 8 bars. And additionally, okay, I have this right here is 2 number 9 bar And don't forget, right, the bottom here is 2 number 8 bars. So that's all the bar information I have. That's all the bar information I have, okay? In the dimension, the clear span length from inside is 25 feet. Okay, from center to center, 26 feet. Okay, and on top of that, right? On top of that, it already tells you it has a moment diagram, right? Moment diagram. So the moment diagram is shown below. Okay, so let's show the moment diagram. So this extension, okay. Now be careful when I draw my moment diagram, profile view. Yes, that's a profile view. It's a side view, okay? This is like a cut. That's like a cut, okay? So let me extend from the inner surface to inner surface, okay? And this is the side, which is the beam. And I have a negative moment on both sides, which is negative 225 cube feet. Okay, and I also have a positive moment. That is 162 cube feet. Okay, so this is my moment diagram. This is my moment diagram. All right, and then I have some parameters, right? So given f prime c is 4 ksi, okay, fy 60 ksi, okay. The dead load tells you already is 1.65 kibs per linear foot. Okay, live load 3.3 kibs per linear foot. Okay, now here, let me note here, okay, 20% of that is sustained. 20% of that is sustained. Okay, all right. Okay, so here, given the construction condition, okay, well, structure condition, so beam supports non-structural partitions that would be damaged by large deflections. Okay, and I tell you that this non-structural partitions, this non-structural part component that is installed, okay, installed shortly after the shoring is removed. Support, right? Shoring is temporary support. Okay, which means this partition added load, okay, partition added load only takes effect after the dead load, only takes effect after the dead load taking effect. Okay, so what does it say, right? What does it say? It's a mouthful, right? What does it say? It actually said this way, right? So we need to actually investigate the long-term deflection, right, caused by the dead load, okay, and the intermediate caused by the live load, which means the full live load, the whole thing. Okay. All right, and then we also have to consider the long-term deflection caused by the sustained live load, which is about 20% of it. Okay, 20% of it. All right, so this is the problem. This is the problem. We're seeking long-term deflection for this structure here, Okay, all right. Now, for a lot of our concrete problem, preparation is the key here. Okay, so before I get into it, right? Before I get into it, let's do some prep work. Let's do some prep work. So what type of prep work, right? First of all, we need to determine solution to solve. First step, we have to determine the effective moment inertia. Okay, and by computing the gross moment inertia IG and the cracked moment inertia ICR. Okay, so first thing first, what is IG? What is IG, right? So let me show you the cross section. Now, up to this point, we haven't shown you the cross section yet, right? So the cross section looks like a T-beam actually. So T-beam cross section. So it looks like this. Okay, and it tells you that has a flange height of 5 inch, a width of 75 inch, pretty wide. Okay, and the web is 14 inches. Okay, and the total height of the beam is 24.5 inch. Okay, so this is the total, right? Total cross section, Okay, all right. So to save some time, you already know how to do the moment inertia for this section, right? You already know how to do moment inertia for this section. So I actually already calculated the centroid of it, right? So the centroid of it actually, or the neutral axis right here. And the distance, right? The distance from the top fiber for the top fiber, okay? And that is what? That is 7.66 inches. But be careful, right now, when I show the section like this and I calculate my neutral axis, right? I'm assuming this is a positive bending moment. Positive moment, okay? This is for positive moment. Okay, now for negative moment, no, let me finish this first. So for a positive moment, this is where the neutral axis is at, right? And the gross moment inertia, right? The gross moment inertia was AIG equal to a 3.3160 inch to the power of 4. To the power of 4. Okay, to the power of 4. All right. Okay, so this is for the T-beam. This is for the T-beam. Okay, this is for T-beam. All right, so that is for the T-beam for the positive bending moment. Now for the cracked session, right? So I'm just say for cracked, for ICR. Okay, again, for positive, ICR positive. I'm looking at a section like this. Okay. All right. And I know it's cracked. So I have to go with a certain compressive zone. So use red, assuming that my compressive zone is within the flange. Assuming the compressive zone is within the flange. And this is KD. Okay. And turns out I can calculate KD. KD is actually 3.73 inches. It's indeed smaller than the 5 inch. So it means it's within the flange. All right. And I tells you that the rebar at the bottom here, and that is NAS, where N is 8. AS is, what is AS here? Two number 9 bars, so 2 plus multiply 1 inch squared, this is number 9, plus a 1.58, which is 0.79 is 2 number 8 bars. Okay, so the total converted or transformed area is 28.64 inch squared. Okay, and the distance between the top and the center of the bar is 22 inches, and the concrete cover is 2.5. Okay, this is for the positive cracked, Okay, however, for ICR, same ICR, negative moment, different color, negative moment. I have to switch my compression and tension zone now, right? I have to switch my compression and tension zone now. So same thing, this is my same exact section. Okay, but my compressive zone is going to be here. Okay, and actually this right here, KD, and equal to 8.65 inches. All right, and now, so on top, I have my converted steel from the compressive reinforcement, right? So this is NAS, and that is 8. And this is what? This is here. Negative moment, okay? I'm talking about this reinforcement here. Negative, okay? Positive, okay? This is negative as well. Okay, so for negative region, the reinforcement changes, right? The reinforcement changes. So this here, 8 times of 4 plus 1.56. Okay, turns out to be 44.48 inch squared. That's the bending, right? That's the bending from the intention. But don't forget, I also have a compressive reinforcement here as well. Okay, where that coming from? This is, okay, so this is negative compressive. This is negative tension. This is negative tension, and this is negative compression. Okay, so for the compression side, I also have to convert, and be careful since this covering the concrete area. So this is N minus 1 AS. So I have A minus 1 must be 1.58, and I have this number to be 11.06 inch squared. Okay, so where does the N coming from? The N equal to ES over EC, where ES is 29,000 KSI, so 29 million PSI, okay, divided by a 57,000 square root of 4,000 in this case, and that is 8. Okay. All right. So what we're looking at, right? So after this section preparation work, right? We check the positive moment in the middle section, negative moment in the at end, positive moment at end for cracking as well, okay, for cracking as well, right? So let's put the number down here, right? So for a positive moment region, okay, what do we have? IG equal to what? IG equal to 33,160 inches to the power of 4. The cracking moment which is FR modulus rupture multiplied by IG divided by YT and equal to 7.5, okay, square root of 4,000, okay, and this is 33160 divided by YT, which is the distance 24.5 inch minus a 7.66 inch, in case you forgot. So just gonna label here. This is the neutral axis. YT is this distance right here. Okay, that is equal to H minus KD. Okay. Okay. All right. So that's my cracking moment. And it turns out this cracking moment equal to 934,040 pounds inches, which is 78 kip feet. 78 kip feet. Okay. So this is the cracking moment, right? And then going back to see my moment diagram. This is my moment diagram. So where's it at? 78 is roughly here, a little bit more than halfway almost. Okay, so that means this is the cracked region, right? The moment exceed that 78, which is cracked. And apply moment, of course, MA equal to 162 kip feet. So once I have that, let me just strictly get a ratio. The crack moment divided by the applied moment equal to 78 divided by 162. I have 0.481. Okay. All right. So I also need to calculate the crack moment for a positive bending moment, which is this fellow right here. Okay. Which is this fellow right here. And I got this number to be a 10860 inch to the power of 4. Okay, inch to the power of 4. Okay, so my effective, my effective moment inertia for the positive region, the middle span, equal to M, and in the middle span, equal to MCR divided by MA to the power of 3 multiplied by IG plus bracket inside 1 minus MCR divided by MA, bracket outside 3, bracket outside ICR, okay? And bring the number in, so there's 0.481 to the cube, and multiply 33160 plus 1 minus 0.481 to the 3, multiplied by 10860. So I got number is 13340 inch to the power of 4 now. Okay. All right. So that is the moment of inertia, moment of inertia at the middle span. This is positive, but this is also at the middle span. Okay. So next, what we're going to do is we're going to calculate the moment of inertia, effective moment inertia for the negative moment region. Okay. So basically, what we did today here is to find this IE here. Okay, this is middle span, and we need to find IE2, IE1, and then to get average IE throughout. Okay, so my time's up. I'm gonna stop here, and we'll continue this on Thursday, which is tomorrow afternoon. Okay, well, sorry, no more. Tomorrow is exam day, right? So we have to continue this on Monday now. Okay, so tomorrow is gonna be the exam. All right, so let me spend 1 minute talking about the exam. I will release the exam at 2 o'clock. And before that, I'll send you an email and how to access to the exam, okay? Now, you will not be supervised. But please do not work in group, okay? And you can use whatever resource you have available for you during the exam time, okay? And the exam is 3 hours. State clearly in my email and also printed on the exam overhead, okay? So I need you to write your name on all the solutions you have, okay? On all the solutions you have, and scan it in terms of PDF, and submit through this online portal, okay? And I'll create an online portal today and send you a link following me as well. All right, okay. So if no more questions, we are going to stop here and we're gonna start our exam. What also I will do is at approximately 1:30 or 1:40ish, I'll send you another Zoom link. And that link will only be active before the exam starts. Okay. If you have any other questions, regarding the exam, you can send me an email quickly during the exam time. Okay. And I will be monitoring my email during that time period to make sure all questions are answered. Okay. But please don't ask me a question about how am I going to solve this problem. Give me some hint. What does it look like that? I will simply not reply emails if you have a question like that. Okay. All right. Okay, if there are no questions, I guess I'll see you tomorrow then before the exam starts, okay? So I sent several emails. Please watch out this email through your mailbox and be ready for tomorrow, okay? Now, if you have any burning questions or reviewing the materials content, please ask for help, okay? So I'm here the whole day for you. So if you need any help on the questions, send me an email and we can arrange a link and I can go over some problem for you, okay? All right? Okay, I think that's it for me. If you don't have any other burning questions, we're gonna stop here and I see you tomorrow, okay? So final call, all righty. Okay, good deal. Okay, so I see you tomorrow then. Thank you very much.